Hello, everybody, and welcome back to Ask Math Anything. Or if this is the first time you're here, welcome to Ask Math Anything. The way this works is you ask any question that you have, usually about math, and what I'll do is I'll choose the questions that have something to do with people who are learning about algebra or geometry, and we'll talk about them. But of course, even though I say algebra and geometry, there might end up being questions about number theory or combinatorics that come into the mix. Let's see what questions we have today. I have a moderation team as well, which helps us to pick questions. But I really do want to see all of these questions which pop in. Okay, so we're already starting to get some questions into here, which is nice. I see that there's some questions which are about proving things. So those are really interesting questions, but I'll say that that's slightly beyond the scope of the session that we're doing here. This session is meant to be as accessible as possible to a wide audience, and so I'm trying to stay away from the questions that would make it too hard for a lot of people. Because, I will say it's an interesting question you ask, but somehow the concept of a proof is something that I don't really want to spend too much time on this live stream. Oh, that's interesting. There's a question here where somebody asks, can you solve for the square root of a number using quadratic equations? Well, that is a quadratic equation. I mean, if you have a square root of a number, let's go and switch to my chalkboard here, just a second. If you have the square root of a number, if you're trying to do something like the square root of 5, well, that's actually a quadratic equation. That's the equation x squared equals to 5, which I can rewrite as x squared minus 5 equals to 0. So actually, square root and quadratic equations are deeply related to each other. But I don't see how you'd be able to use the quadratic equation to solve for the square root, because it amounts to the same thing. However, your question is still interesting, because it turns out that you can define interesting numbers as the roots of some polynomials. In fact, the number I, the square root of minus 1, that comes from the polynomial. Polynomial is just something that has many, or well, one or many terms, with x multiplied together by itself or added together with itself, multiplied by some normal numbers. But if I write down something like this, x squared plus 1 equals 0, well, then the solution to that turns out to be I and minus I. But it is a useful concept that you can make these numbers as the roots of these equations. Oh, let's talk about that one. Shah, what is the square root of I? Well, that's a good question. Well, what should this be? I mean, we couldn't take the square root of minus 1, and therefore we had to invent a new number called I. So maybe because we have the square root of I now, maybe we need a new number. Let's call it J. Well, actually, it turns out that you can talk about this. You can talk about this. And what I'll do is, this is related to what's called complex number multiplication. But I'm going to draw a funny picture. Okay, it's going to look like coordinate axes. And what I'm going to do is I'm going to draw a point right here, which is exactly 1 unit up. And it's on this vertical axis. And right there, I'm just going to write I. Now, this is a notion which is useful in studying complex numbers, or these kinds of imaginary numbers. And it's where you draw the imaginary number on an axis, on a pair of axes, well, in the plane, where the horizontal part is telling you what is the real part of it, and this vertical part is telling you the imaginary part of it. And now there's something which is beyond the scope of this live stream, so I can't prove it to you here. We don't have enough time. But it turns out that there are ways to take the square root of a number, because when you multiply two complex numbers, what happens is that their distances from the origin multiply, and their angles from the origin add. And so what I'm going to do is I'm just going to intentionally draw another distance 1 line, length 1 line, and it's going to be at 45 degrees. So, well, even if you don't understand complex numbers, can you tell me where the tip of this point is? If I wanted to go at 45 degrees up, well then, where is this? How far across is it, and how far up and down is it, if that hypotenuse is 1? Well, this is a famous kind of 45, 45, 90 right triangle. So a 45, 45, 90 right triangle, this would go 1/2 across and 1/2. No, it wouldn't. It would go 1/2 square root 2 across and 1/2 square root 2 up and down. And that's because there's a 1, 1 square root 2 triangle. And this is just like dividing by square root of 2. I realized that what I just did here skipped a step. Let me do something simpler, okay? So if I have this thing which is 1, this distance here, and I want to know what are each of these two things, with a 45, 45, 90 right triangle, when you go from the hypotenuse to one of those legs, you divide by square root of 2. So I'll do that first, okay? So if I divide by the square root of 2, this would be 1 divided by square root of 2, and this vertical part would be 1 divided by square root of 2. I actually had also rationalized the denominator. I had actually thought of multiplying the top and the bottom by root 2 to get root 2 over 2. That's another thing that you could write for the same thing. But now that I know I go 1 over root 2 across and 1 over root 2 up and down, well, now I'm just going to label that dot up here with 1 divided by square root of 2 plus 1 divided by square root of 2i. Using this mentality that somehow with this way of writing the complex numbers on these coordinates, how far it is across is telling you what is the real part, and how far it is up and down is telling you the imaginary part. But now, look what happens if I multiply this by itself. Well, let's try. 1 over square root 2 plus 1 over square root 2 I times itself. 1 over square root 2 plus 1 over square root 2 I. Well, if I expand that out, what I'll get is I'll get the first thing times the first thing, which is 1 over square root 2 times 1 over square root 2. That's 1 over 2. I'll also get 2 copies of the same thing, because the first thing here times the second thing there is the same as the second thing there times the first thing there. So let's see. One of them would be 1 over root 2 times 1 over root 2i. The root 2 and the root 2 make a 2, so you'd get a 1/2 I, okay? And there's a second copy of it, 1/2 I, plus another copy of 1/2 I. And the last thing you get is this 1 over root 2i times 1 over root 2i. Well, the 1 over root 2 times 1 over root 2, that gives you 1/2. Oh, but the I times I gives you -1. So I'll just write like -1 over 2 here. I should probably have just said -1/2. Let's do that. That looks better. -1/2. Now you get some canceling. Look at that. The half cancels with the -1/2. So it's gone. And you just have 1/2 I plus 1/2 I. So that's just I. So there you go. This number here is the square root of I. There's more coming, don't worry. This is a square root of I. So this is one of the square roots of I. And the way I came about with how I chose this number is I used the fact that when you multiply complex numbers, the lengths multiply. The distance between the complex number and the origin, that multiplies by whatever that distance is for the other complex number. And since I wanted to get a distance of 1 in the end, I would just take the square root of 1, which is 1, and that's how far I go here. And because the angles add, so if I have a complex number, this angle is 45 degrees. When I multiply by another number, complex number whose angle is 45 degrees, I'll get a complex number whose angle is 45 plus 45, which is 90. So I divided the angle by 2. Now, I said this was one of the square roots. There's actually another one. So there's something about quadratics, in that quadratics can have up to 2 roots. Sometimes the roots are repeated. But over here, if I wanted to say I can have up to 2 roots, can you see something else I could have used? And the hint is, whenever you're dealing with complex numbers, whenever you're dealing with square roots, well, there are positive and negative square roots. So there should be something which is all the way on the other side, which is the negative of it. And there is. If I go the other way, this is minus 1 over root 2 minus 1 over root 2i. And this guy, when I multiply by itself, actually you can already see, if I just did that thing, it's just going to be minus and a minus. Of course, minus times minus is plus, and you'll get the same answer. And if you think about it from the point of view of adding the angles, it's also interesting. Because let's look at the angle here. This angle here is 180 plus another 45. What in the world is that? Well, I don't know. I don't actually need to work that out. You see, that angle is 180 degrees plus a 45. But if you square that complex number, you'll multiply that, you'll add the angles, and so that means I'll get 2 of them. That's like how far around it would go if I multiplied this by itself. And look, 2 times 180, that's 360. Plus 2 times 45 is 90. And so it's perfect, because if I add up the angles, I'll get a 360, which is a full revolution, plus another 90. So that works too. So that's the answer to square root of I. Turns out that there are 2 numbers here, this one and that one, which are the square root of I. More questions. Wow, I see that we have people who are watching this from India. Welcome. Somebody's asking how to qualify for INMO, which is the Indian National Mathematics Olympiad. So I have a lot of respect for my counterparts who are the coaches of the Indian National Math Olympiad team. My understanding is that they'll have some competitions. So you'll have to enter those competitions. Quite possibly it's similar style to the US, which is where some parts of the competition involve calculating answers to weird questions, and some part of the competition involves proving things. The calculating stuff, you can look at the old problems and teach yourself how to be good at those by actually trying to work on those questions yourself. And if you get stuck, you can look at the solutions, but only look at them for hints, and then use your own creativity to try to invent how to solve those questions. It doesn't matter if you don't have a coach. It doesn't matter if you don't have a book. What you need to do is you need to try the questions, and when you get stuck, just look at the solution for a little hint of an idea and go back to thinking. And that same method can help you learn how to do the proofs as well. There are, of course, other kinds of ways that you can get good at these if you take classes, but I'll say even if you don't take classes, it will work too. More questions. Okay. Somebody has asked, explaining how lifting the exponent works. Sorry, that's beyond the scope of this live stream. That's more for the Olympiad level. Okay. Let's see. What else can we have here? Wow. So I'm going to my moderator team now because they have picked a lot of different questions. What is this? Okay, there's a question from Anonymous Pi, since we seem to be on the topic of square roots and multiplying things up. Anonymous Pi says, what is the value of? Okay, I'm trying to read this carefully. There's a square root sign, and inside the square root sign, it is... So I'm having trouble with this. So I'm going to write down a question first, and I'll ask Anonymous Pi to please clarify, is this what you actually mean? But what I see here on what the moderators pasted is that there's a 3 minus 2 square root of 3 parentheses squared. But that's under a square root. And then plus the square root of, and then now here I have 3 plus 2 times the square root of 3 squared. Anonymous Pi, is this the question that you want me to answer? I'm just asking this because there's like squareds under the square roots. Okay, well in that case, don't we know? If you want to do the squareds and the square roots, you just cancel them, right? So then the answer, shouldn't the answer just be 3 minus 2 square root of 3 plus 3 plus 2 square root of 3? And then the answer is just 3 plus 3 is 6. Well, no, it can't be that simple. It's not that. And the reason it's not that is because actually the square root is always the positive square root, the non-negative square root, right? So don't worry, I knew that wasn't the answer. But so the thing is that the square root sign is only getting the positive square root. Non-negative square root. 0 is okay. And so what we need to worry about is, are these actually positive numbers or non-negative numbers? Well, if I look at this, 3 plus 2 root 3, that is totally a positive number, okay? Because I added positive stuff together. So that part's okay. But how about this other part? This other part here, I have 3 minus 2 root 3. So somehow I sort of remember that square root of 3 is about 1.732. And already you see that you have trouble. Because if I double that, 2 times this is 3.4 blah blah blah. And if I have 3 minus a 3.4 blah blah blah, that's no good, because that's negative. So in that case, if I have a negative thing squared, and then square root, actually the answer is the absolute value. It's the positive version of it. If you want to think about it, just imagine you did negative 4 squared and then square root. Well, that becomes the square root of 16, which is positive 4. So in that case, I need to have the positive version of this, and that would be 2 root 3 minus 3. Okay, so that means that the answer is just 4 root 3. Is that correct? Uh-oh, somebody said, oh no. Does that mean no? Just checking. Somebody said, oh no. But I am not sure whether the oh no is talking about my thing or other stuff. Anonymous Pi says it's correct. Yes. Okay. And the main thing is just to be careful of the signs, positive and negative signs. Those things also happen, by the way, if you ever have inequalities. Be very careful of inequalities if you try to divide by a variable like x. If x is negative, you need to flip the direction of the sign. So be very careful. Some person said that it was from earlier, the oh no. All right, let's get more questions. Oh no, some people got trolled by this on the AMC 10B. All right, be careful. Actually, in general, if you ever see a question that looks suspiciously easy, you should be aware that it's probably a trick question. Okay, more questions. Oh, neat! Toady Master has asked, how do we know that pi is 3.14 ... when there are no perfect circles in this world? So you're right, there was no way to just measure around the perfect circle and then experimentally be like, yes, I know it's 3.14. So the way that you can know the 3.14, a long time ago, the way that Greek and ancient mathematicians were doing it, is that they just said, what is pi anyway? Pi is the ratio of the circumference divided by the diameter. And what they actually did is they did math problems, because there's no way to make a perfect circle. So for example, you can estimate it by taking a circle which is like, taking a circle and then making some shape around the circle whose perimeter will be close to the circumference. For example, if this is my circle here, hey, here's a shape there we go. So I mean, the perimeter of that square is going to be similar to it's going to be something like the perimeter of the circle, right? And in fact, I can write it this way. The circumference of the circle, I have an inequality. Circumference is actually less than this perimeter of this square. Okay? But you know, if I take the diameter of the square, how does the perimeter compare to the diameter of the square? Well, actually, the perimeter of this, if the diameter is this d, let's call it d. If the diameter is d, can anyone tell me what's the perimeter of this square if the diameter is d? Well, it's just d plus d plus d plus d, 4d. So the perimeter here is 4 times the diameter. And by the way, this thing already gives you an inequality about pi, because pi is the ratio circumference divided by diameter. So if I divide by diameter, circumference divided by diameter is less than 4, which is good, because you know that pi is less than 4. Okay, so this way we can find that the pi is less than 4. But there are other things we can do too. For example, I can draw this shape. Now, do you see that actually the circumference of the circle is going to be bigger than the perimeter of the diamond? In fact, the diamond is taking shortcuts, effectively. If you imagine that there was this nice path that you're supposed to walk on, this nice maybe sidewalk that's around a nice circular field, the nice way to do it is to walk around the sidewalk, and then somebody decides to just cut corners. That's a bad analogy, because that person's making corners. But that person decides to just cut across the grass by doing this walk, okay? But in that case, I can write inequality on the other direction. The circumference is bigger than the yellow perimeter. Well, now, here's an interesting question. If I have that yellow shape and the diameter is d, what's the yellow perimeter? I guess we better draw in the diameter. Here's d. uh-oh, it's not so easy anymore. Last time we just said, hey, look, it's a d, so there's another d, and these are all d, so it's 4d. But here we have to do the Pythagorean theorem or the 45, 45, 90 right triangle thing again. Remember that if you take this is the hypotenuse of the 45, 45, 90. If you divide by square root 2, that's how you get one of these legs, one of these shorter sides. So each of these is d divided by square root of 2. But there's 4 of them. So that means that the perimeter is 4. Let's write it here. The yellow perimeter is 4 times d divided by square root of 2. You can actually write this thing more nicely, because 4 is actually, you can divide 4 divided by root 2 like this. 4 I can think of as 2 times 2, and then times d over root 2. So now, if I take one of the 2's and divide by a root 2, what's left is another root 2. So it's 2 root 2 times d. Hooray! So that now I know that this thing here is 2 root 2 times the diameter. So what I can find out if I just divide by the diameter is that circumference divided by diameter is bigger than 2 root 2. So I've just found out a very nice inequality. Pi is between, let's write the pi more tidily. Pi is between, on one side, 4. That's the wrong color. That's still the wrong color. Come on, yeah. 4. And on the other side, it's 2 root 2. This is satisfying because it's true. Square root 2 is about 1.414. So just remember, square root 2 is about 1.414. So this 2 root 2 is like 2.828. And good. You see that we got this like 3.14 thing is sandwiched in between these two. And so the ancient mathematicians, what they did is they actually thought about taking a circle and then drawing more and more and more sophisticated polygons around them and inside them. And then that was letting them sandwich the value of pi. I'm actually not sure how many digits they calculated pi to that way. In the modern way, what we do is we don't draw all of these polygons. We use some things in calculus that let you express pi as infinite products or infinite sums, and then we just calculate a whole bunch of these terms, and then we actually get that 3.14 thing. Okay, great, nice question. Oh, there's a follow-up question. Why is there not perfect circle in the world? Because the world's not perfect. I mean, if you even look at the Earth is not a perfect sphere, you know. If you take the Earth, it's not a perfect sphere because actually the Earth rotates around the equator. No, it doesn't. The Earth rotates around the pole, and the equator is like this thickest part. And because of physics, it actually causes that part to get oblong. Sort of like how if you ever look in the movies of people throwing up the pizza, and the pizza dough is like doing this thing, and it elongates out that way. So basically I'm explaining that it's actually quite hard to get things to be perfect spheres or perfect circles in this world because there are too many different forces. Is there a planet which is a perfect sphere? No. Any planet, well, okay, I shouldn't say no. I think no. I'm not an expert here, but I think that most planets are spinning in some way. And so as soon as you're spinning, that actually starts to cause there to be some kind of this elongation in a particular dimension. And if you're wondering why would there be spinning, I believe that actually comes because you have, as all the little tiny pieces of matter are coming together, they're all coming together in slightly different angles as they're being pulled in. And the chance of you having everything come in just right so that it all balances in a space where there's no friction anyway to stop you from spinning is that, well, it's just going to have a little spin in one direction or the other or a big spin. Somebody just asked, are atoms perfect spheres? That is an extremely deep question because atoms are actually not just, they're not hard balls, you know. Like an atom actually is, they're even, somehow the cloud of electrons is where the electrons themselves aren't even in specific places. So I'll say the atom is not actually a perfect sphere. I think the concept of where the atom's charge might be distributed, the electron's charge might be distributed. Actually, that's not perfect spheres either. If you go and learn chemistry, you learn about things called electron orbitals. And then you find out that actually those electrons aren't even just all like spherically distributed. Okay, great. It's complicated. Okay, more questions. Let's see. It looks like we have just gone all the way into physics. Let's see what my moderators picked up while I was busy on these tangents. Ooh, what's this? Okay, so I see a question here that has something to do with circles and quadrilaterals. It's going to take me a moment to understand what the question is saying and then write it down, okay? It says that there's a circle which is circumscribed around a quadrilateral. So if that's the case, that means there's a circle and there's a quadrilateral inside. Whenever I have something like that, you draw the circle first, because otherwise it's just too lumpy. All right, so there's a circle. Now the next thing you do is that there's a quadrilateral inside where there's two sides which are 160 and two sides which are 36. So let's see, let's try to draw this. AB is AD is 160. Let's see if this works. The numbers seem like very symmetric. The numbers seem like very symmetric, so I want to draw a picture that's also kind of symmetric. Okay, so it was A, B, C, and D, sort of symmetric. AB and AD are both 160. And we have that BC and CD are 36. And this circle, by the way, has a radius of 82. Okay. And the question says, what is the area of the quadrilateral? Okay, area. Well, when I look at this, I say, is there anything that I can draw in to represent the radius? And as you can see, there's some nice symmetry here. It's the same above and below. That means that AC is a diameter. So let's draw the diameter in. So that means that is double of 82, which is 164. Wow. That means this diagram is very much not to scale, because if that's 160 and that's 164, presumably they should be like really skinny. But okay. Oh, interesting. This thing is then telling me, I want to make sure I didn't make a mistake, because if that's actually the diameter, right? If that's the diameter, well, actually, because of the way that the angles work, there's a nice fact from geometry, which is that this is supposed to be a right angle. Is it? Let's find out. Because what I'll do is now I'll try to divide out these by a common factor. So I see this is a multiple of 4, that's a multiple of 4, and that's a multiple of 4. So if I divide out the 4 from each of them, then that would tell me that there's some kind of a right triangle in the world which does this. 9, 40, and 41. Really? Actually, it is one. If you want to know, you can just double check. There are a couple of ways to double check, by the way. One way to double check is just to say, all right, Pythagorean theorem time, 40 squared plus 9 squared, and hope it works. I'll show you another way just to check that this is actually a legitimate right triangle. The other way is to say, well, why not just check what the difference of the squares is? Because if the Pythagorean theorem, since the Pythagorean theorem is true, if I take 41 squared minus 40 squared, that should be, well, if it is a right triangle, that should be 9 squared. Is it? Is there a nice easy way to take 41 squared minus 40 squared? There is. It's a difference of squares. So if I have difference of squares, that difference is actually their sum times their product. 41 plus 40. 41 plus 40 times 41 minus 40. Oh, it sure is 9 squared, because 41 plus 40 is 81, and that's just 1. So it's good, it's good. This is very nice. So that means that we haven't made a mistake. This is actually the diagram. And then the question just asked, oh, what's the area of the quadrilateral? Well, then I just need to add up two triangles, right? And in fact, they have the same area. So it would normally be half of the base times the height, but times 2. So I don't even need the half. So the area is just equal to, well, I'll write it this way, 2 times, because there are two triangles, half times the base, which I'll call 40, times the height, which is 9. That wasn't too bad, because the half and the 2 cancel. I just get 40 times 9, which is 4 times 9, 36, 360. And that's it. Okay. No, Somebody said no. Is there a mistake? Uh-oh. Mistake. Oh, there's a huge mistake. There's a huge mistake. I forgot that it's bigger. Oh no! Okay, it's bigger. No, over here I just got distracted. This is not what we're supposed to do. I scaled down. Yeah. You guys are right. Oops, mistake. Let's fix this. Okay, it should be times 1/2 times, let's write the big things now. It should be times the base times the height. 160 times 36. Okay, times 160 times 36. Okay, so now it's a little bit more work because I have to scale it up again. Or rather, I have to multiply bigger numbers because thus the 2.5 still cancel. But I have to do 160 times 36. Do I have any clever way of doing that? Not particularly. Let's do it. Oh yeah, here's a fun thing. I usually like to write the smaller number underneath. But look, I'm doing something weird. I'm saying that there's a extra 0 dangling off. This is not actually how you should do multiplication, but it works because I'm just imagining I'm multiplying these numbers, and I'll tag a 0 at the end. So I'll do 6 times 6, which is 36. 6 times 3 is 18, plus 3 is 21. Ah, that's good. 216 I expect, because 6 times 36, that's 6 times 6 squared, so it should be 6 cubed. And then I do the 1 times 6, 1 times 3, add, and I get 0, 6, 7, 5. 5, 7, 6, 0. And that is the answer. Okay. What else do we have here? We have about 14 minutes left, so let's see what kind of questions we can pick. Proving areas of proving things. Again, unfortunately for this live stream, because I'm trying to be as accessible to a wide audience as possible, we're not going to focus on the proof type questions. Okay. And I see somebody asked how to derive the formulas of permutation and combination in an easy way. I actually do that in my combinatorics classes. For example, we have our online school. It's inside there. But I'll say that there are lots of other places that you can find that, so I won't talk about that here. Okay. What's here? Ooh, here's a question. I don't know the answer yet. Let's think about this. Okay, so this is a question which is by Ellen W. And it says that a box has 4 cubes and 1 sphere. Box has 4 cubes and 1 sphere. Okay, but now they're playing a game. Who's they? Well, there's 2 people. Ava and AJ take turns. Ava and AJ take turns. And what are they doing? They're picking a shape out of the box without replacement. Picking a shape out of the box without replacement. That just means that shapes are disappearing from the box. And now it says whoever picks the sphere first wins. Whomever, I'm not sure. Whoever, is it whomever or whoever? I'm just going to write whomever because that's what I'm used to. Whomever picks the sphere first wins. And the question is, what's the probability that Ava wins? Okay, well, when you look at something like this, it's like, what does this mean, pick the sphere first wins? There's only 1 sphere anyway. So this is neat. Okay, this is making me think that it would be a great chance here to teach about this concept of what's called fictitious continuation. You see, probability is a subject for which symmetry is really important. Oh, somebody just said AJ goes first. Oh, yes. It's actually very important to know who goes first. Yes, that's very important. So let's go and add this. Whoever, they take turns. Also, Ava doesn't go first? Well, people are telling me AJ goes first. Take turns picking a sphere with box. Whoever picks sphere first wins. Oh, yeah, there's space here. AJ first. Goes first. I don't have space. AJ goes first. Yes, it works. AJ goes first, okay? And so now the question is, what's the probability that Ava wins? So what I want to talk about is this principle of fictitious continuation. And fictitious continuation is where you say, hey, let's go and replace the problem with a different problem. And it will turn out that once you stare at it, you see that the answer is the same. So the fictitious continuation I want to do, why it's called continuation is, in the original problem, as soon as you pick a sphere, game over, GG. But what happens here is that we're just going to say, keep playing. Play all the way. Pick all 5 things, okay? So the fictitious continuation here is they always play until everything is picked. And now, if you think about it, what does it mean first person to pick the sphere? There's only one sphere anyway. There's only one sphere. So it's that the winner is, after they play until everything is picked, the winner is whoever got the sphere. Whomever got the sphere. Aha. But at that point, then if you think about it, I just have 5 things, okay? And if I have 5 things and they're just randomly picking, suddenly what matters is like at which step did the sphere get picked, right? When we're asking what's the probability that Ava wins, this is asking what's the probability that on Ava's turn she picks a sphere. So actually what we're asking about is the probability that the sphere is picked well, Ava moves second, or fourth. And the answer is the same. Okay, so now I just have to know if I've got these 5 things and they're being picked in some random order where all the orders are equally likely, well, at that point, what's the chance that the sphere ends up in position 2 or 4? There's only one sphere. By symmetry, it has equal chance of being in position 1, 2, 3, 4, and 5. So in that case, there are 2 of these turn numbers on which the sphere could be picked that cause Ava to win out of 5 total. And so the answer is just 2 divided by 5. Nice question. Okay, what else can we do? Bye, thanks for coming. Oh yeah, thanks for coming. Let's see. How are we doing on time? We still have some time. What else do we have here? Seven minutes. I'm just trying to look at all of these to see which one should we pick. Oh wow, somebody has a neat question of using calculus to find approximate values of square roots. Oh, that's pretty good. I will say that's very good. The square root of 103. But the problem is calculus is beyond the scope of this live stream. But it's a great idea. I'll just say the concept there is you want to estimate the square root with a straight line. I'm awfully tempted. So here's what I'm going to do. I don't have time in 7 minutes to do that one, but I will just simply say if you want to estimate the square root of 103, well, you can use the fact that I can draw the square root function. The square root looks like this. Yay, there we go, that's square root of x. Okay, and then now somewhere there's like 100. Here's 100. This is not exactly drawn to scale, but that's 100. And then this is the square root of 100, which is 10. Now, if you want to go and estimate what's the square root of 103, if you could just figure out how to approximate this by a straight line. It looks pretty much like a straight line, and that particular straight line, it turns out that it has a particular slope. The slope of that line is like 1 over 20, I think. Is that right? Is that what I want to say? Yeah, it's 1 over 20. So this thing has a slope. So this thing has a slope of 1 over 20. And you can use the fact that the slope is 1 over 20 to go and estimate what would happen if I just went over to 103 and just moved along the yellow line instead. Okay, great. So don't know what this is? Don't worry, this is calculus. We won't focus on this. Calculus is a part of math, that is true. All right, what else can we do here? Oh, I'm sure that people know what the slope is, but the concept of the calculus, the one place that I used calculus in my head was estimating what is that actual slope. And the slope of that is this 1 over 20 because of some fact from calculus, okay? Let's keep going. Oh, a puzzle. This is a good thing to end with. Juliet Z. Suppose that P is a 2-digit number. P is a 2-digit number. Q is the same digits in reverse order. Same digits in reverse order. These are always cute questions. But now it says if I take p squared minus q squared, that's a non-zero perfect square. And the question is, what is the sum of the digits of p? Okay, so whenever I see something like this with 2 digits, I say, I think I need some variables. And I always like to use the 2 digits to be t for tens and u for units. I don't like to say t for tens and o for ones because o is a really lousy variable. Okay, so what I'm going to say is that p as a 2-digit number, that is tu, but t is the tens digit, so that's 10t plus u. Did that make sense? The tens digit times 10, that's the number of tens, plus the units digit, that's p. But then q is nice. Q is 10u plus t. Because I just flipped those digits. Because the digits of p are t and u, so I flipped them, okay? So now if I have this, I can just actually write down what this thing is. What's p squared minus q squared? Well, p squared minus q squared, that's just 10t plus u squared minus 10u plus t squared. Expansion time. So here I'm going to use this common expansion, which is something we also saw previously in this course and also today, which is that if you take 10t plus u squared, that's the square of the first plus double of the product of these two plus the square of the second. So that's just going to be 100t squared plus 20tu plus u squared. That's from this first part minus 100u squared plus 20ut plus t squared. Ah, well, this is convenient because the 20tu and the 20ut cancel. And now I can even collect like terms because I have 100t squared and I have a minus t squared. That's 99t squareds. Oh, and the u squareds are plus 1 and then minus 100, minus 99u squared. So now I know that this is 99 t squared minus u squared. Well, how could that possibly be a perfect square? In order for that to be a perfect square, 99 is a 9 times 11. 9 is already a perfect square. I like that. But what this information tells me is that since I don't need to worry about the 9 anymore, that's a perfect square part, that means that 11 times t squared minus u squared has to be a perfect square. So what I now know is that 11 times t squared, let's factor it. T squared minus u squared is t minus u times t plus u is a perfect square. Okay, How could that ever happen? Well, when you look at this, you're like, well, t and u, those are digits, so I don't have much freedom. In fact, what I'm already seeing is that how can I ever get rid of the 11? If I want a perfect square, where can the 11 possibly go? Could I have a tens digit minus a units digit be 11? No, because they're all digits. You're only going to get, like, the biggest thing you'd ever get is like 9 minus 1, which is 8. That means that the 11 comes from here. This is nice. So that means that the only way to get this perfect square is if t plus u is the multiple of 11. You see, we can't have t minus u be 0. That's a multiple of 11 also, but we're saying it's a non-zero square. So that means that t plus u is some multiple of 11. Could it be 22? Good luck. You can't find two single digits that add to 22. So that means that t plus u is 11. Oh, and that's what the question asked. This is such a cute question. The sum of the digits of the number, well, it has to be 11, because that's what we just got here. We're done. It's 11. And if you look at it, you're like, you might also be able to even come up with a number that works. You see, because if I want that this 11 and that 11, well, those multiply, that's good. If I need the whole thing to be a perfect square, I need to have two numbers that add to 11 where their difference is a perfect square. And there's an easy way, 6 and 5, right? It could be like 6 minus 5 is 1. That's a perfect square. Anything else we can do? We couldn't have a difference being an even number. So the next opportunity is 9. Nope, you won't get 9. So the number is actually 65. And that's it. All right. Well, unfortunately, we are out of time for today. I hope that you guys had some fun with this Ask Math Anything. I'll be back next weekend. Oh, will I? Actually, I'm not sure I'll be back next weekend. Next weekend, I'm supposed to be in Boston. I go around the entire country on weekends nowadays. Last weekend I was in Kansas City. This weekend it was in New York City, actually New Jersey and New York. Next weekend I'm supposed to be in Boston. I'm not yet sure exactly when I'm getting home. If we'll have one, I'll post it on this channel. But I'll definitely see you soon. Take care. Bye-bye.